Alrighty, we're back at it. This is the Wolken Way. Today we're doing basics of functions and their graphs. So we got how to tell if it's a function, how to solve a function for y so that you can determine if it's a function, how to evaluate functions, some word problems, and domain and range from graphs. We'll do domain and range from equations in a couple of lessons. Anywho, so that's what we're going to get started with today. So let's take a look at this. So the definition of a function, the real official definition of a function is that each member of the domain, which keep in mind domain is the x values, corresponds to exactly one member of the range. So you cannot have a situation where a number x is going to two different y values. So here's the little memory device that we have for remembering if something is a function or not. So first of all, you're going to think of the x's as the boys and the y's as the girls. And this would be boy 2 asking girl 0 to the prom. This would be boy 1 asking girl -3. And then this would be boy 3 asking girl -3. This kind of situation is okay. It's still considered a function because the x value is corresponding to exactly one y value. It just so happens that two different x's go to the same y, just like two different boys can ask the same girl to the prom because she's super sweet. She has the best personality ever. So this type of situation here is an example of a function. However, let's take a look at B, where we have boy number 3 asking girl -1, okay. Boy number 6 asking girl 2, okay. Boy number 3 is asking another girl. He's asking girl 0. This is the situation where one member of the domain, 3, does not correspond to exactly one y value. It's going to two different y values. So in our little analogy, that's one boy asking two girls to the prom. He's kind of a player. It's not cool. Pick one and go with it. So that's my little analogy for how you can remember boy, girl. And the really cool thing about all this is you have domain. It goes with the x's, and like I just said, it's also our inputs. I didn't just say that, but I just wanted to put that up there. It's the things that we input. It's x, and it's the boys. And then on the other side of that, we have the range, which is also the y values or the outputs. And in our little analogy, it's the girls. So what you notice is that all of these within their row are alphabetical. These comes first. So domain is before range, x is before y, inputs before outputs, and boys before girls. So how would we respond to this? I know this one doesn't say to explain your reasoning, but sometimes you have to, so I want to make sure you get that. So I'm going to put yes, and I'm not going to put because every boy is only asking one girl to the prom. I'm going to say that same thing, but using proper terminology. Yes, because every boy, no, I can't say boy, because each member of the domain corresponds to exactly one value of one member of the range. And you can see I got that wording from the definition, so just have something like that. A lot of people also just memorize that if you see the same x value repeated, not y value repeat is okay, but if you see the same x value repeated, then it's a function. If somebody was really trying to be, then it's not a function, but if somebody was really trying to be tricky, they could write 3, 0 and 3, 0, and you would see two 3's, but because it's going to the same exact y value, that would still be considered a function, but who would do that? So this one was no, and we're going to say the x value of 3 corresponds So this one says it can only be exactly 1, so we're going to say here's our disproof because it corresponds to more than 1. Value of y, or y value, so it corresponds to -1 and 0. Okay, so that's how you tell if something's a function just from a set of points. Now we're going to look at equations. So when you have an equation, x is the independent variable in most situations, so we're going to call that the input, and y is the dependent variable or the output. So the independent variable isn't determined by some other variable, whereas we have to know x to be able to find y. So to determine whether or not an equation is a function, so we just did points up there, but to determine whether or not an equation is a function, the first thing you're going to do is solve the equation for y. And this is called putting y in terms of x, meaning you have y equals and everything to the right is x. And then if a given x value produces 2 or more values of y, the equation is not a function. So let's work through some of these so that you can see that. You might have an idea, but let's look at this. Y equals -x plus 5. So I solved it for y, and when I plug in an x, is there any way I could get 2 different y values? No. It doesn't matter what value of x I plug in. I'm always just going to get one y value. So in that case, each member of the domain corresponds to exactly one member of the range, so that equation is a function. Let's take a look at this one right here. To solve this one for y, my first step is to move the x to the other side, and then I'm going to square root both sides. When I square root both sides, I have to do the plus or minus because the square root wasn't originally in the problem. So what that tells me is I'm going to plug in one x value, do a little math, and then I'm going to take the positive case and the negative case. So I'm plugging in one x and getting out 2 y's, which does not meet the conditions for being a function. I would try C and D on your own. Some people pick up patterns, but I just want to make sure that they are picked up all the way. So this one, we start to solve for y. And again, don't forget, anytime you have to draw in that square root, you have to do the plus or minus. So in this case, it's no again. Well, students start making connections and they start to think, well, there's a square root there, so automatically it's no. But did I have to draw that square root in? No. So the cool thing is this one's already solved for y, but I'm going to plug in some number x, do a little math, and then change its sign. That's what this equation says, so I'm not making a positive case and a negative case. So this one is, in fact, a function. Okay, so again, this lesson goes over a bunch of basics of functions, so we'll be moving right along in this. So, next one, example 3 says evaluate. So we have this function, and we have to plug these values in. So this is big for me here. You have to make sure that you realize f of x, this is our input. Wherever there is an x on the other side, those are also inputs. So we don't just add the -5 in, we have to take the x out and input the -5 because this says the input is -5, so everywhere there is an x, we do that. So students don't have a hard time with this with A and B. The time they have a harder time with this is C because they think this says x plus h. So what they'll do is they'll just add a plus h. I didn't write it because it's not good, but they'll just write it to the end of the function, but that's not what function notation is saying. This is saying this is your input. So when I give you a new input like -5, everywhere there was an old input, you take it out and replace it. So f of -5 is equal to -5 squared minus 2 times -5 plus 7. So that would be 25 plus 10 plus 7. So f of -5, when the input is -5, the output is 42. Okay, so that's the answer for that one right there. Draw a little line here to give myself some room. So the next one is f of a. So in order to do f of a, my new input is a, so everywhere there was an x, it's going to get replaced by an a. So f of a equals a squared minus 2 times a plus 7. So that simplifies to a squared minus 2a plus 7. So f of a equals exactly that. It looks very similar except for our variable changed. Like I said before, it's letter C where students start struggling because it's really testing your understanding of how to evaluate functions. So there's two x's here, so I'm going to remove those two x's and plug in this x plus h. So f of x plus h looks like this. X plus h squared, so that's for that one, minus 2 times x plus h. That's me taking out that x and plugging in my entire new input, x plus h. And in fact, I'll just kind of use this yellow pen to highlight what I'm doing. So I'm going to go all the way back here and just show you when we changed this, we ended up changing that and that. Okay? And the same thing happened over here. When I changed this, it changed it here and here, but those numbers are still coming from right there. And then finally, here's that x plus h. And when I did that, I'm taking the x plus h and the x plus h, and then I'm still missing my little plus 7, so I need to get that back in there. Okay, so now I need to simplify this. The other ones were a little easier to simplify. First of all, I am not gonna kill any puppies here. I'm gonna make sure I FOIL that out. Distribute my negative 2 to both the x and the h, and then simplify from there, and I can't do anything else. There's no other terms to combine here because none of them are exactly alike, so that is my answer there. Moving right along. Okay, so the next one is kind of what we talked about before, y in terms of x. So these are functions where y is written in terms of x. So what you can see is that this is solved for y. So, and the x's are all on the other side. Now let me give you some counter examples. These are functions where y is not in terms of x here. So you can see the y, this one has x's on the same side. So you want to solve for y. That's what y in terms of x means. So we did ask you to comment in any observations, but since we are not doing this in class, we're going to say y or f of x is isolated on one side of the equation. If y is in terms of x. One other thing, might say this a little differently. You can say the x's are on the opposite side of y when y is in terms of x. I mean, that makes sense. Y is in terms of x. Terms of x are like 2x squared, 3x. So y in terms of x would mean you have y equal to all these x terms. Okay, so example 4, it just goes right back to what we were doing, except for I'm not asking you if it's a function. I'm asking you to put y in terms of x. So we just have to solve all of these for y. So what I was saying before is a lot of times students like to divide by -3 there, but a lot of times when I see fractions going to be present, I like to multiply it by the reciprocal because it's the same thing. And so here, because this is 3 over 1. And I have to do the opposite to make sure it's positive y when I simplify. And then this would be negative 2 times negative 1, which is 2, and 1 times 3. So, and then this one would be negative 2, because 6 times negative 1 is negative 6 divided by 3. So there's that one. Let's see, on this next one, again, you guys could pause the video and do these yourself just to make your life easier, and then just check your answer. Sometimes students don't like this one. They start going x squared minus 8x plus 16, but really, you can move this whole quantity. All you got to do is make it negative when you move it to the other side. Whoops, I put an equals when I meant to put a plus. Okay, so there's that. This one, I'm just going to add the 2x, but I'm going to make sure I put it by descending powers of x. That's just good math procedure. So the 2x is going in between because this goes x cubed, there's no x squared term, and then we have x to the first power. And then this one, literally just going to add the whole square root to the other side. You can put it in front or you can put it in back. I'm going to put it in back because the square root is to the 1/2 power. That's another way to write a square root, and this is to the first power. So I feel like that's more standard form than the other way. Alrighty, now we're ready to move on. You guys can see it says 1.2 and 1.10. For some reason, they decided to do all the word problems at the end of this section in 1.10, and we just felt like it would better fit in the section that it's currently in. So what we're going to do is just add it to this section right here so that we don't have to do a whole section on just word problems. So you have 140 yards of fencing to enclose a rectangular garden. So you have here, so you're going to enclose the whole garden. We'll talk about this more in a second. Express the area, so you want to circle that, of the garden as a function of one of its dimensions, x. So it's saying y is a function of x. So here we go. We also have 140 yards of fencing, which that amount is actually going to be the perimeter. So perimeter. Why is this important? So we've created a little chart to help you remember. We're going to add to this chart in the next chapter, so that's kind of why we start it in this chapter. So you just make a little plus sign. I guess it's not little, it's actually rather big. And the first thing that you're going to do goes in this box right here. So I'm going to write the directions in the box this time, but when we go to do problem 2, we're just going to know what goes in there. So you are going to write the equation using what they are asking for. So in this equation, they're asking us to express the area of the garden. So our equation is going to be x times y. We're going to call this x, we're going to call that y. Okay, then over here in step 2, so it's like the coordinate grid kind of, right? So quadrant 1, quadrant 2, quadrant 3, quadrant 4. Haha, math class, cool. Then we're going to write the second equation with the first sentence usually, but we'll call it the other given info. So like I said, that's usually the first sentence. So we're asked to find the area as a function of one of its dimensions. That's just saying write the area in terms of x, and right now this is x and y, so it's not in terms of x. So we're going to take this, and because we are talking perimeter, we know that's 2x plus 2y, and because we have 140 feet of fencing, or 100 yards, that's going to be 140 to go all the way around that. In step 3, we are going to take this equation right here and solve for y. So I'm going to move that negative 2x to the other side, and then I'm going to divide by 2 or multiply by 1/2, whichever one you want. and I get that. So still haven't written this function in terms of just x. So what I'm going to do now, which is step 4, again, we're going to leave this right here open because we're going to be doing something with it in the next chapter. But you come back up here for step 4, and you are going to substitute this y in. So substitute in y. So we get the area is equal to x times, and here's that y, negative x plus 70. And why do we want to do that? We want to do that because now we have it all in terms of x, which was the job. So for now, to answer the question, we can write a of x. We can use this notation now because it's all in terms of x, equals negative x squared plus 70x. And we will want it multiplied out for when we do this step right here, so that's why I'm doing it. Hopefully in the next one we can fit this still up in that quadrant, but for now we're good. Okay, so again, first box just goes like, okay, what are they even asking for? Okay, they're asking for area, equation for area, formula for area, A equals x times y. Okay, cool. What's the given information? Pretty standard for word problems to identify your given. Okay, it's 140 yards of fencing. Okay, my connection is that if I have 140 yards of fencing to enclose this region, it's going to be the perimeter. So it's going to be 2x plus 2y equals 140. Then with those two equations alone, I can solve this one for y, plug it into where the y is in the area formula, and I get area in terms of x. Sweet. All right, move it over. Move it over, flip it over. I'm getting delirious. Too many videos. Ha ha ha. Okay, on the back side, it's the same kind of problem. We're just applying it to a new situation. So you have 600 feet of fencing, okay, to enclose a rectangular field. Okay, however, oh no, one side of the field lies along a canal and doesn't require the fencing. So here's our rectangular area, and here's the canal. And so because one side doesn't require fencing, when we talk about the perimeter, we're not putting fencing back there. So let's take a look at the chart. I'm going to kind of do it this way to give myself more space. So express the area, okay? Area equals x times y, okay? What's the other piece of information? 600 feet of fencing, but I don't go up here, so I just have one x length and two y lengths, and that's going to equal 600. So I just want to pause and tell you guys, they also like to do these ones right here. They like to get crazy and tell you that you have enough fencing to enclose the outer region, and then you're going to divide it in half. So this would be like a little kid's playground and a big kid's playground or something like that. So if that was the case, my perimeter, or the formula that would go right there, how much fencing I would need 2x plus 3y. So those are all the different adaptations of this particular type of problem. So next, once I have that, I solve it for y. So then I get y equals negative 1/2 x plus 300. I know you can just write this as negative x over 2, but get in the habit of seeing dividing by 2 as the same thing as multiplying by 1/2. It'll make your life easier. Then I'm going to take this and plug it in up here. And then I'm going to multiply that. And because it's all in terms of x, I can use that notation now. Area in terms of x, negative 1/2 x squared plus 300x. And that is the answer right there. Alrighty, so those were the word problems, and now we are moving on to domain and range of a function. So again, domain, the x values, range, the y values. So domain is kind of like the width, and range is kind of like the height. So we're going to take a look at this graph and see what the domain and range is. So we're going to use interval notation too, so we're going to get to practice what we learned in P9. So take a look at this. Using interval notation, identify the domain and range. Okay, so domain. For this particular problem, if I just look at the x's, the x to the left, the lowest x, you can include it because it's a circle, would be -5. And the furthest to the right x is down here. So you can almost trap it between lines if you can trap your graph. You're saying that's how wide the graph goes. So that would be 2. And then the range, lowest y value, so now we're going bottom to top. So least to greatest with domain is left to right. Least to greatest with range is bottom to top. So the lowest number down here is also -5, just coincidentally. And what's the highest number? Oh, here, and that's +3. Okay, pretty cool. All right, let's move on to the next one. Alrighty, so it looks like the graph might be trapped here. Oh, but be careful. Arrows in math, graphs imply that this is going on and on and on, and this is going on and on and on. So as it's going up and down, it's also going to go wider. So the domain and range are all real numbers. And it can take on any value of x and any value of y. So the way we write that in interval notation is -infinity to infinity. All right, let's mix things up just a little bit. Oh, we got an open circle. Do you guys see it? So with the open circle, what you're going to want to watch out for is making sure that you use a parenthesis instead of a bracket. So the furthest to the left would be an x value of -4. And the furthest to the right, hey, this thing keeps on going down, but it's also going to keep on going to the right, so that's infinity. Now let's take a look at the range. So bottom to top, this graph is going to keep going down, so -infinity. And then what's its highest y value? It's way up here, but it can't equal it, so it's 5. Okay, moving on. This is so fun. Now we have an absolute value graph. That looks nice. Okay, left to right, the smallest x value is -4, and it can include -4. And the biggest y value, x value is 4, but it can't be 4 because it has an open circle. Now don't get tricked by this range. Bottom to top. As they come in from -infinity, what's the lowest y value? It's right there. It's -3. And unless it's an open circle, you can assume that it's touching. So I know it's not a dot because it's not an endpoint, but it is going to be touching -3. And then this graph keeps on going higher and higher until it gets to +3, but it can't be +3 because it has an open circle. All right, I like to make things a little trickier for you guys right now. Let's take a look at letter E. So I'm going to start with the range this time, just because I want to. So the range, no. Let's go back to the domain. No worries. Okay, so with the domain, I'm going to go negative and coming in from the left, it's going from -infinity. And then I'm tracing this graph as I'm going left to right. Oh no, there's a hole in the graph at 1, so it can't equal 1. So, don't know why I put that there. We have to exclude 1. It can't equal 1, but then it could equal any number after 1. So like, for example, it could be 0.9999999, but when it gets to 1, it's not there. It's undefined, and then it picks right back up at 1.0001. So we'll pick it right back up, and then it keeps on going to infinity. Now, here's the really interesting thing about range. The range is from bottom to top. So you start going up, and you're going up, and you're going up, and you're like, hey, Vulcan, right here, it can't equal y equals 1. But you have to be careful, because does the graph at some point have a coordinate of 1? So right here, this coordinate is 1, 1, but it can't equal that 1 right there. But over here, this coordinate right here is 3, 1, and it's going right through it. So guess what? If it goes through it, if the graph takes on that y value at any time, it's included in the range, okay? So for this particular one, even though in the y, in the x, if you look, is there any other x value that equals 1? No. So you excluded 1 because there's no x value of 1 in this graph. However, there is an x value, or sorry, a y value of 1 here, even though there isn't one here. So the range is negative infinity to infinity. So if the graph of the function touches the y value, it is included in the range, even if there is a hole in the graph. Okay? So let's move on to this next one. So let's see. Left to right, we're going to start with domain. We got a hole there. So -5, right? And then you might want to say it's going to go -5 to -2 and then -2 to infinity. Here's this x value right here of -2, right? Sorry, -1. It's at -1. I keep saying -2. What I want you to notice, does this coordinate, what's the coordinate of that point? It would be 1, 4. Does it touch 1? Yes. Even though here, which we can call that coordinate like 1, 1.25, it doesn't touch, we're still going to include it because at some point the graph touches it. So we're including 1. So we're going to go past 1 and it keeps on going. So we go -5 to infinity. And then the range for this one, let's go low to high. So bottom to top. Bottom looks like it's right here. That's the lowest point on the graph right there. And that has a y of -3. And then it keeps going up, right? And then right here, you're like, okay, but then there's this big jump. But look at this, guys, over here. That arrow implies that that graph is going to keep going. So even though right there, which has a y value of 1.25, if I come over here, does some part of the graph have a coordinate with the y value of 1.25? And that answer is yes. So because it does, it's included. So we are not going to change anything about the hole right here in our range, and we're going to keep going up, up, up to infinity. So all in here where you think, oh, there's no y values, well, there actually is parts of the graph over here with those y values. Fancy. All right, these last two problems help us with intercepts. So I'm going to write the domain and the range down, and then I will talk about it. So this one is -infinity to 2, then from 2 to 4, and then from 4 to infinity. And this one, the range is -infinity to infinity. So these graphs that we're looking at that are more challenging are called piecewise functions, and we'll actually learn how to graph them pretty soon in this chapter. But what I want to point out is this domain, left to right. First we're kind of looking, okay, all x values. Right here, when I get to -1, you're like, oh, there's a hole in the graph right there. But look at this part of the graph fills that hole, if you will. So it has an x coordinate of 1. So we're going to just pretend like that hole isn't there. Then we keep going, keep going, keep going. Oh no, there's an asymptote right here. That implies that this graph isn't going to cross on either side. So it means that x cannot equal 2. So we have to show that the graph gets really, really close to 2 from the left and the right, but doesn't actually equal 2. All right, we're still going left to right, and then we come up to this point right here, and then there's a hole, and then it continues. Is there any other part of the graph touching an x value of 4? No, so I exclude it. Range, low to high. So you're like, okay, Vulcan, look, there's an endpoint right there. The range isn't -infinity to infinity. You're wrong. But what is happening with this piece of the graph? Those pieces are going to -infinity. So it does go on. And right here, if you're like, okay, well, what about this hole right here? Don't you exclude that? Well, look at, there is actually 3 different parts of our graph that have that y value. So even though at that particular place on the graph it doesn't have a y coordinate of 1, all those other places do. And the same thing happens with this hole right here. Even though this doesn't have a y coordinate of 3, that does. So if at any point it has that y value, it's included in the domain and range. It wouldn't make sense not to include it. Okay? Okay, last one on here before we are done with this thing. We have -infinity to 0. and then from 0 to infinity. So let's talk about that real quick. So left to right, negative infinity, right here is an excluded x value, but wait, there is a point. Even though it's not in the same line, it's still part of the graph, so it does get included. So we don't do anything, we're just going to skip over it. Then we get to 0. Is there any other point of our graph having an x coordinate of 0? Nope, exclude it. Go to here, whole, oh, this one has an x value of 4, even though this doesn't, so I still have to include 4, and it keeps going. What about the range? The range is going to be from -3 to infinity, because the lowest point on the graph is -3, and then you come up to this point right here, and you think, okay, -3, and that right there, it can't have a value of -2, but that part of the graph has a y value of -2, so I don't exclude -2, it just stays in there. Okay, keep going up. Then I get to here. Oh, look, at 1, this point has a y value of 1, and then you're like, okay, keep going up. Oh, what about this one? Hey, Wolken, I think your answer is wrong, because this one right here, did you think this point was filling it up? No. What I know is that this graph keeps going. So even though this point right here isn't responsible for, or does not have the same y coordinates, somewhere out here, even if it's not in my graph, that arrow implies that it's going to continue to go up. It will, and it's going to increase to infinity. So -3 to infinity. And that, my friends, is 1.2, 1.10. Have a great day.